An ellipse. The term ellipse is actually a Greek word, which means a falling short or a deficiency. In geometry, this name reflects the fact that an ellipse is a conic section that results when a plane intersects a cone at an angle that is not perpendicular to the base, leading to a shape that falls short of being a circle or parabola. If we stretch or squish a circle, we get an ellipse. Now let's do a little experiment. We will need a serious notebook, so people think we know what we're doing, of course. Paper, 2 thumbtacks, some dental floss or a string, and finally a pencil. And now what we've all been waiting for, the experiment. The first thing that we're going to do is place these 2 thumbtacks into the paper as firmly as possible and make sure that they are next to each other. Let's focus on these for now. Let's focus on them so much, in fact, that we call each of them the focus. So we have F1 and F2. Together, we would call them the foci. Now, let's put the floss around it and let's pull it with the pencil to see what it creates. We are making sure that the string is being pulled to its maximum the entire time. Of course, we will be making some mistakes here or there, maybe 1 or 5, but it's nothing we can't erase, hence the pencil. What we just drew is the set of all points so that the sum of the distances from each pencil point to the 2 thumbtacks, which we know as the foci now, they stay constant. All of these points make up an ellipse. Now that we have our ellipse, we can define it by 3 things. The first 2 things are known as the foci, which are demonstrated here by our thumbtacks, which we so meticulously place into this paper. So we have focus point number 1 and focus point number 2. So what is the third thing? Well, the third thing is actually a distance. So let's say 2a. Why 2a, you may ask? Well, let's take a point on the ellipse. This is a completely random point and has no preference. I had no preference as to where this was. So let's call it P1. And let's look at the line segments from each of the foci to P1. So as you can see, we have this line and this line. If we were to add this, we would get a value. So let's call that value 2a. Okay? So if we were to add these 2 lines, and we get the sum and we get 2a, and we choose another point, let's call this one P2, again at a random point. We look at these distances now, and we add this one and this one. It would actually be equal to the sum of these lines as well. So that's what's cool about ellipses. If you choose 2 foci and a distance, an ellipse is actually a set of all points, such that all points, the sum of its distances from each foci is equal to the original given distance. So if we were to get another point as well, let's say P3, it would be the same. So you add these and it would be equal. So that's the entire idea essentially. So let's look at a line that passes through the foci. So the line that passes through the foci of the ellipse is called the major axis. So this would be the major axis. And let's look at the midpoint of the 2 foci. So let's say here, for example. So that's just an average. I have no idea if that's actually midpoint. The midpoint of the 2 foci is the center of the ellipse and midpoint of the major axis as well, right? So a line drawn perpendicular to the major axis at the center is actually called the minor axis. And that is all you need to know for now to then be able to dive into the mathematical section of ellipses. Alright, so now we had a little fun demonstration about ellipses. We are going to get into the more mathematical aspect. And again, what is an ellipse? So an ellipse is the locus of points in a plane such that the sum of distances from two foci, which are the fixed points, is constant for all points on the curve, as shown in the demonstration before. So what is a locus exactly? A locus is the set of all points satisfying some condition. So the locus could be the shape of the line, circle, or curves, etc. So this is the locus, which is the ellipse in this case. We can think of an ellipse as a circle that has been squished or stretched in one way to give it the shape of an oval. Okay, so we went through all this already, so let's move on. Now, the equation of an ellipse depends on if that center of the ellipse is the origin, which is 0, 0 or not. So the different scenarios is the ellipse with center 0, 0 or ellipse with center HK, which is any two numbers. All right, so let's go through ellipses with center 0, 0 first. So we have the horizontal ellipse with this being the equation, and the vertical ellipse with this being the equation. So the equation of ellipse with center 0, 0 is x squared over a squared plus y squared over b squared is equal to 1. Remember, 0, 0 for horizontal ellipse, where the major axis is the x-axis. So again, for horizontal, the major axis is the x-axis. For vertical, the major axis is the y-axis. And the only difference here is that you're interchanging where a is. So a squared and b squared basically flipped for these two, for horizontal and vertical, when the center is 0, 0. All right. Now, for ellipses with center HK, the horizontal ellipse, remember, the center is not 0, 0. The equation of ellipse with center HK is x minus h all squared over a squared plus y minus k all squared over b squared. So notice these are the coordinates, h, k, and these are negative signs, very important to remember. And again, for the vertical ellipse where the major axis is parallel to the y-axis, we can see that they just switched. The b squared and a squared are switched. Okay, and that's how we know the equation of an ellipse with either center 0, 0 or center HK. So now we're going to look at an example. The example states to find the equation of an ellipse with center minus 1, 2 and passing through the points 0, 6 and minus 7, 3. The first thing that we notice is that the center is not 0, 0. So it's of the form HK, where h is minus 1, k is 2. So we can recall that the standard form of the equation of an ellipse with the center HK and its major axis being the x-axis is this. So what we're going to do is substitute the 2 points that we have, so 0, 6 and minus 7, 3, as well as the center into the standard form of the equation, and we're going to get 2 equations. So we're going to substitute 0, 6 first, then minus 7, 3. Make sure you are aware that these are negative signs, so be careful. And we end up with these 2 equations. So now you are all probably familiar with simultaneous equations, and we are going to solve them simultaneously to be able to find the values of a squared and b squared. Okay, so we have the 2 equations that we can solve simultaneously to get the values of a squared and b squared. So as you all are familiar with the method of elimination and substitution, in this case, we're going to try to eliminate one of the values. Okay, so we're going to multiply 1 by 36, this equation, we're going to multiply it by 36 because we want to isolate b. Okay, and this will get rid of a to be able to isolate b. All right, so we do that and we get a third equation. So now we're going to subtract equation 2 from 3, and you realize how it gets rid of the a, which is what we wanted to. We wanted to eliminate the a. That's why it's called elimination. Okay, so then we end up simplifying to get b squared is equal to 115 over 7. So now that we have b squared, we can substitute it into either equation, which is this one or this one, to solve for a squared. Of course, always choose the simpler equation to substitute it into. In this case, it looks like either one, so it doesn't matter. So let's just choose number 1. We substitute b squared into equation 1, and then we end up solving for a squared, because remember, this is the only variable that's left to be solved for, and then we get a squared is equal to 115 over 3. Okay, therefore the equation of the ellipse is, remember, we substitute everything into these. Now we're simplifying, and we get the final equation with all the values here that we used to get the final equation of the ellipse to be that. Now we're going to go through another example to understand this topic even better. This example states to determine the center of the ellipse as well as the lengths of the major and minor axes. So we have 5x squared plus y squared minus 30x plus 40 is equal to 0. So what we're going to do is put this into a recognizable form, aka the form that we learned before, to be able to determine the values. So in this case, the center and these lengths. So we're going to follow these steps to do so. So the first step is to group the terms with the same variables and move the constant to the right. So now we see that we have to factor out 5 of this so that the coefficient of x squared is 1 within the brackets. So when we do that, we're going to complete the square for each grouping, but in this case, we're only completing the square for x. And remember, when you're completing the square, whatever you add, you must subtract to keep things even. Remember, this is just to put it into our desirable form. So when we do that, we are going to simplify even more and divide throughout by 5. And then remember, where we have to recall the standard form of the ellipse. Well, the equation of an ellipse with center HK is this, which is what we were looking for. We were trying to put it into this form, and we did so. So now we can see that a squared is equal to 1 and b squared was equal to 5. So we know that a is equal to the square root of 1 and b is equal to the square root of 5. So because b is larger than a, the length of the major axis is 2b and the length of the minor axis is 2a. So we have 2 multiplied by the square root of 5 for the major axis, and 2 multiplied by the square root of 1, which is 1, for the minor axis. And we know that the center would be 3, 0. And that's how you solve that question. The next thing we're going to learn how to do is how to sketch an ellipse. And we're going to learn how to do so by doing an example, because what better way to learn than to actually do it? So the example is asking us to graph this ellipse. So to do that, we are going to put it into a recognizable form. So we're going to rewrite the equation in standard form first. So we're going to start by grouping the terms with the same variables. Then we're going to factorize it so that the coefficients of x squared and y squared is 1, right? So when we do that, we are going to complete the square for each grouping. And for the terms involving x, we will use 8 over 2 squared. And for the terms involving y, we'll use minus 10 over 2 squared. And remember, we need to subtract what we add to be able to make things even. All right. Then we're going to simplify everything and divide throughout by 18 to put it in the form to get the equation of an ellipse. Divide throughout by 18. Why? Because we're trying to make this side 1. So when we get it into this form, we can then know what the center A and B are. So we're going to determine that the center is minus 4, 5, and A is the square root of 9, and B is the square root of 2. So when we know these values, we're going to use A and B to mark the vertices left and right of the center, as well as vertices up and down from the center. So we're going to see that our vertices, remember we have 4 of them, 4 main points, 1, 2, 3, 4, as well as the center. And we get along the minor axis minus 4, 6.41, minus 4, 3.59, and minus 1, 5, as well as minus 7, 5 along the major axis. So when we get all our points, all we're going to do is plot them. So after plotting them, we connect all these dots, make sure you put the center as well, and then there you have it, your sketch of an ellipse. Now we're going to learn about parametric equations of ellipses. So again, remember that parametric equations are in terms of other variables. So in this case, x and y. So the parametric equations of an ellipse are x is equal to h plus a cos t and y is equal to k plus b sine t, given that the Cartesian equation of an ellipse with the center hk is the standard equation that we learned before. So again, parametric equations are called as such because they are written in terms of other variables or parameters. This is an example of how parametric equations might be involved in a question on the test. So this example states that given that the parametric equations are x is equal to 5 plus 4 cos t and y is equal to 3 plus 2 sine t, find the Cartesian equation of the curve. So what do we notice about these equations? One has cos t and one has sine t. So again, remember that everything is connected in some way. All right. Now, in this case, we know that from our trigonometric identities that sine and cos have a relationship. So let's use that to our advantage. These parametric equations are written in terms of sine and cosine. We know that their relationship is sine squared theta plus cos squared theta is equal to 1. And we're going to apply this to our parametric equation to find the Cartesian equation of the ellipse. So writing x in terms of cos t, why are we doing this? To be able to put it into a form which we can recognize, okay? So when we find cos t, we're going to square it to be able to get cos squared t. All right, so remember, we're getting this again. We're going to do the same thing for sine t, and we're going to get sine squared t. All we did there was make sine the subject of the formula, sine t, and then we squared everything. So when you square the left-hand side, you must square the right-hand side because everything must all be balanced out. Then we're going to add 1 and 2, these two equations, to each other. We add the left-hand side to the left-hand side and the right-hand side to the right-hand side. And we know that from our identity that this left-hand side is equal to 1. All right, so when we do that, we can recognize something very quickly. Also note that the major axis is the x-axis and the minor axis is the y-axis. So from this, what can we do? That's it. That is the equation. So the equation of the ellipse, we're just putting it into a more recognizable form, and that's it. And we can see that the center is 5, 3. Now, some things to note just in case they bring it on the exam. We're going to look at tangents and normals in ellipse. So the gradient of the tangent in ellipse is minus b cos t over a sine t at the point P, a cos t, b sine t. Again, things to just remember in case. The equation of the tangent is given by y over b sine t plus x over a cos t is equal to 1. The gradient of the normal to the ellipse is a sine t over b cos t at the point a p, which is a cos t, b sine t. We have to recall that the gradient of the tangent multiplied by the gradient of the normal is equal to -1. And the equation of the normal is given by, I'm not going to try to read this out, but you all take note of it in your minds and your books, okay? So let's look at an example. This example states to find the equation of the tangent to the ellipse, x squared over 16 plus y squared over 4 is equal to 1 at the point P minus 2 square root of 3, 1. So remember that this is of this form. So we can easily find A and B, which in this case is 4 and 2 respectively. We need to recall from before, again our little notes, that the gradient of the tangent to the ellipse is minus b cos t over a sine t at this point. So remember the point is this in this case, so we're going to equate them this is that, this is b sine t. So a cos t is equal to minus 2 square root 3, and b sine t is equal to 1. We're going to substitute the value of a and b in this case, and we're going to solve for cos t and sine t. So now that we have the expressions for cos t and sine t, we're going to substitute them to find the gradient of the tangent, and using the formula we learned above. When we do that, we can easily find the gradient by substituting and then simplifying. Therefore, the equation of the tangent at this point is going to be, and then remember all we're doing is substituting all our values into the equation, simplifying it to get our final answer, the equation of the tangent being the square root of 3 over 2x plus 4. And that's it. And that's the end of the video. I just wanted to do this video in case something does come up in the future, because I have seen it mentioned on the syllabus once or twice, which is very, very rare. I haven't seen it in any past papers thus far. You guys could correct me if I'm wrong, but I haven't found any, therefore we don't even have a past paper section. But just for the students that want to be prepared in any case, I made sure to include it in the video.